Hi, and welcome to another Algebra 2 flip lesson where my cat Dexter is going to say hello and then skedaddle off the table. Tonight we're going to have a combination of a couple of things going on, and the first one is going to be talking a little bit about modeling functions on the coordinate plane. And one particular thing I want to point out is the notion of how to set up your axis correctly. So sometimes when we're modeling problems, one of the things that we encounter that becomes a difficulty is plotting out the coordinate plane. So in class we had talked a little bit about having y-intercepts that were off the grid in terms of being able to see them and view them on the graphing calculator. So we have to be able to adjust the window screen, but more importantly, when we're graphing it, we have to be able to adjust the scale that we use. So an important aspect of graphing correctly is to plan it out properly, know how many units you need on your x coordinate and your y coordinate before you plan the graph, and then use your scale in order to plot it out. So for instance, say you have a y-intercept of a function that's at 500. If your y-intercept is way up here at 500, then I need to see what goes on beyond that point. So I'm not going to necessarily put 500 up here. I may put 500 a little closer to the bottom and then plot the scale accordingly. You may wish to put a little strike through your bottom of your graph indicating that I'm not starting this at 1. I might start it at 100 and then base it on that in order to plot the y-axis accordingly. Your y-axis could have different intervals than your x-axis. Say we're talking about seconds. I can plot that and say that's 1 second, and that's 2 seconds, and there's 3 seconds. And these do not have to be the same amount of units. So whatever you label your graph when you're graphing, you would want to tell the reader of the graph what it is that you're creating the scale by making markings and what this is representing as well. Okay, that's pretty much all I'm going to say about graphing and modeling right now. We're going to be modeling other functions. Linear modeling is not so much a big question on the Algebra 2. It's more of an Algebra 1 type of problem, but we will be doing some exponential modeling. We're going to do quadratic modeling and such, so all of that will come up. And when we do that, we'll be doing more graphing. Okay, the second thing I want to talk about, looking for my eraser, is inverse functions. We had discussed a little bit about the inverse functions in the function unit, and I just want to touch upon it in terms of the point-slope formula. So yesterday's lesson we did point-slope formula of a line. So let me just throw out this equation. I'm going to switch to yellow chalk because it's brighter. Y minus 5 equals 2 times x plus 1. Okay, this is the point-slope form of a line. Okay, looking at it, I see a point and I see a slope. So take a moment, think about what the slope is, and jot down what you think the point is. Okay, you should have written that the slope is 2, and the point has coordinates -1, 5. Now you might encounter a question that says, given this equation of a line, what would be a point on the inverse of the function? Well, inverse, as you know, switches the x with the y. So a point that's on the inverse of this function would switch the x and the y. The y becomes the x, and the x becomes the y. And you would answer 5, -1. Now, what if I was given the problem of find the inverse function using the point-slope form? So if I am asked to find it, first thing that I do is I have to switch the x and the y. So each y becomes an x, each x becomes a y. I'm going to multiply both sides by 1/2. Cancel my 2 and the 1/2 there. And so 1/2 times x minus 5 equals y plus 1. Confirming the x-coordinate of 5 and the y-coordinate of -1 as being the points on the line. I could also subtract the 1 from the other side of the equation and get y alone and putting it into that form. Other things I could do is distribute the 1/2 through. If I want to know what the y-intercept is, I could look strictly at the 1/2 times -5 and then subtract 1 to find out where on the y-axis that this function hits. Okay, so those are some things that we can do with inverse functions. And as you recall, every inverse function is a reflection in the y equal x. So once it's graphed, you have to make sure that that is actually looking like a reflection in the y equals x. And remember, functions that are not one-to-one do not have inverses that are functions. In order for a function to have an inverse that's a function, it must be one-to-one. Okay, recalling a concept from last unit. All right, so with the rest of the remaining time, I'd like to just concentrate on piecewise functions. Now, a piecewise function means that I'm joining two or more functions together, and I'm defining them over a specified domain. For instance, if the function f at x equals x minus 1 for values that are between -4 included and -1 excluded, and the function -2x plus 4 for values -1 included all the way to +4, and I'll just include that one too. Okay, so some of the things we need to do is be able to look at this and figure out what the y-intercept of the function is. Figure out what the zeros of the function are. Be able to graph it, be able to look at it. Okay, so I'm going to start with graphing. Now when we're graphing something like this, what we want to do is we want to plan out the x-axis first. So you want to take your x-axis and section it off according to the given domain. Now, between -4 and -1, I'm going to be drawing that line that has a positive slope. And between the values -1 and 4 on the x-axis, I'm going to be drawing this line, which has a negative slope. Okay, so I take my values, -4, I'm going to darken this spot right there, to -1, and that means that in this section of the graph, in this domain, I'm going to be drawing this line, okay? So one of the ways that you can do that is I can just plug in the values, -4, -3, -2, and even -1, and I can plug it in here and find out what my y values are. So let's quickly do that. That's easy enough. -4 minus 1 is -5. Let me do that in yellow. And so we have the first point. This point is included because I see the extra line here, so extra filling there. I go to x is -3. -3 minus 1 is -4. -3 down 4. Also filled. I put in -2. At -2 it's -3. A little bit off. I'm not on graph paper, so it will look a little off. And now at -1, I'm going to put it in here, but what do you notice? It's not included. So I need to graph up to that point, but I may not graph that specific point. So at -1, I'm at -2, but at that point, I need to draw an open circle. My graph, this segment of this line needs to be graphed right up to that point. But again, do not fill in that point. It must be represented by an open circle. Now that's all I graph for that top function. The second function is graphed from -1 to 4. So -1 is sectioned here. I need 4 1, 2, 3, 4. I'm going to mark that off because that's where I'm going to end it. And now I'm graphing this function. This function has a y-intercept of 4. I could see that because it's in my slope-intercept form. And at -1, -1 is included. If I plug -1 in here, I have -1 times -2, which is 2, and then plus 4 more, which is 6. So I need to go up 6 and over to -1. Now this point will be a filled point, and I want you to think to yourself, what's the reason why only one of them could be filled and not both? So why is that filled and that not filled? And why can't they both be filled? Well, the answer is because if they were both filled, it wouldn't be a function. So I need to only have one of those points included and not the other one included. Now, if we see this has a slope of -2, I could use the slope and graph the remainder of the function and see that it has a 0 of the function right here at +2, a y-intercept of 4. I'm going to graph it. I'm going to keep going until I hit the last piece on my domain interval, and I'm not going to put an arrow. That's it. It's got a domain, this section to this section, a full domain from -4 to +4, and the range of the function goes as low as this point, which was -5, and it goes as high as this point, which was 6, +6. Okay? And that's how to graph a piecewise function. Now, they don't connect. So recall for a moment that when they don't connect, it's called a discontinuous function. Okay, the second problem is a piecewise that's already graphed, and you have to figure out what the equation is. So I'm going to quickly draw this piecewise function that I've prepared. I'm going to give you the coordinates because, of course, I'm not on graph paper. It may not look exactly perfect. So I'll give you the coordinates of the endpoints. Okay, so this graph looks like that, more or less, looks like that. Okay, so I need to write now the piecewise function that mimics this graph. So first thing you need to do is figure out how many functions are we talking about here. So this piece is 1, so that's going to represent one linear function. And before we write it, let's define its domain. So f at x is going to equal 3 different pieces. I need a nice big bracket. The first piece is going to have a domain from -4 to 2. Now, I'm going to write it at including that -4, not including the 2 on the right. Okay, and we're going to pause there. The second piece, and I'm going to just try to peel that away for a second. We know the axis is there. It's just in my way. The second piece goes from a domain interval of 2 to 5. If I don't include the 2 there, I can include it there. And it goes to +5. And the second domain, the third domain, is going to go from 5 to 7. So from +5 to 7. I'm going to include it there and not, I'm also going to include it there because it's the endpoint. Okay? Now I just got to come up with the functions that this matches. So in order to get the functions, we have different ways that we can do that. The first way would be to evaluate the change in the y's divided by the change in the x's. We have 2 points, we can find a slope. So by now you should have noticed that this is a -1 slope with a y-intercept at the origin, so it's a direct variation. And so y equals negative x, I'm going to put a colon to separate the domain. Y equals negative x is the function that represents this piece. And that piece I will just highlight in red. Okay? So the first function, y equals negative x. All right, now it's horizontal. My y's stay the same. The x's change, the y's always stay. So what does y always equal? Y equals negative 2. And that's defined from 2 to 5. So y equals negative 2. And the last function has a steeper slope and it's positive. And it goes from 5, negative 2, all the way up to 7, 4. So if you calculate this, the slope, you could do the change in the y, 4 minus negative 2, or 6, over the change in the x, 7 minus 5, or 2, and 6 divided by 2 is 3. So my slope of that line is 3. And if I pick one of the 2 points, I can write it in the point slope form. So I'm going to write it with the point 5, negative 2, and use the slope 3. So it's y minus becomes plus 2 equals mx times x minus 5. I can choose to leave it in this form and place it over there, or I can subtract the 2 from this side. If I do that, I'm going to get y equals 3 times x minus 5. And I'm running out of room here, so I'm going to move this domain interval over. And minus 2 more. So 3 times x minus 5 minus 2. And y equals, okay? And I do not even need these y equal pieces. Once I have each one of them, it's kind of redundant because I have f at x equals. And so when you want to write the piecewise function, you just write it with the functions y equals negative x from negative 4 to 2, y equals negative 2 from 2 to 5, and y equals 3 times quantity x minus 5, all divided minus 2 from 5 to 7. And that's basically how to write a piecewise function. This one is continuous because as you move along, it is a continuous function. Doesn't have any breaks, doesn't have any jumps, and therefore it's continuous. Okay. The last piecewise function I want to show you is a quadratic with a linear. And the function f at x equals x squared minus 4 and negative 1/2 x plus 5. The first function, I'm going to define that one from negative 1 to 3. And the second function, I'm defining the domain from 3 to 8. Again, remember, if I'm not including the 3 here, then I include it here. To include it in both places could mean that I'm creating a non-function because it would fail the vertical line test. Okay, so let's quickly graph these. This is quadratic. It's quadratic translated 4 units down. So I'm going to, I don't think I gave myself enough room there. Let's try that axis again. So it's a quadratic function. I'm going 1, 2, 3, 4 units down. That's the first point, the initial point for x squared minus 4. Now I'm graphing it. Let's get the domain all squared out. From negative 1 to 3. So from negative 1 to 1, 2, 3, in this domain, I'm going to plot the rest of the quadratic function. So when x equals -1, -1 squared is 1, 1 minus 4 is -3. That's a filled circle since it's included. At +1, it's also here. Remember the symmetry over the axis of symmetry, which is the y-axis. And the next point I'm going to graph is x equals 2, only on the right, not on the left. The graph begins there and goes this way. When x is 2, y is going to equal 0. And the last point I'm going to graph is going to be an open circle because at x is 3, the point is not included. But I have to graph it right up to that point. So put 3 in here, you get 9. 9 minus 4 is 5. 1, 2, 3, 4, 5. And that's going to be an open circle, and I'm going to draw that right up to that point and stop. Okay, the second function is -1/2 x plus 5. Now, that has a y-intercept of 5, but that's not included in the domain. So I could, and some people do this, very lightly sketch what it would look like, kind of plot it out, and then erase this. But I kind of like to just use the domain that's given, and if you have to, you go to your graphing calculator, you go to your table, you get those values, and you kind of figure it out. Or we could just kind of figure it out. 1, 2, 3, 4, 5, if that's my y-intercept and I have a slope of -1/2, I go down 1 and over 2, still not included. Down 1 and over 2 is my first point that's going to be included in this graph. I have to go to 8. 1, 2, 3, 4, 5, 6, 7, 8. That's where I'm finishing the graph. So the next point from here, I go down 1 and over 2. And now I'm at 6, 2. And one more time, down 1 and over 2. And my last point is 8, 1. And again, I could at any point just put those values into my equation. Oh, I'm not including 8. I need an open circle. At any point in time, I could just plug those values in here. If I put 8 in here, -1/2 times 8 is -4. -4 plus 1, plus 5 rather, is 1, and that's why I'm up to that point. Do the same if you want for this point and for this point. Okay, now this is graphed up to whatever the value is when x equals 3. But that's kind of like in between. So I'm going to plug in x equals 3 because I need a closed point for that. -1/2 times 3 plus 5, which is -3/2 plus 10/2, just so I can add the fractions easily, which gives me 7/2, which is basically 3.5. So at x is 3, I go up 1, 2, 3 and 1/2. And I'm going to graph that segment. Okay, now that's discontinuous. So the big question then becomes, what would I need to do? How would I need to shift this function in order to make it continuous? So I want to take this point and I want to somehow figure out how to move it so that it's on top of that point. Okay, so the way that you do that is you look at the y value of that point. That point had a y value of 3.5. This point of the quadratic had a y value of 5. To go from a y value of 3.5 to a y value of 5, I need to move up 1.5 points. So if I take this function and I add 1.5 to 5 and make it 6.5, then I can change it and make it a continuous function. Every point would follow, and each point would go up by 1.5 units. So it's a translation of 1.5, which would then make this a continuous function. Okay, so that's all there is tonight. We kind of covered a lot. The modeling and the inverse was review. The piecewise function, we had touched upon it in the past, and a little bit more of review. We're going to practice these concepts tomorrow in class, and we're going to move from there straight to systems of equations and 3 variables with 3 equations. So that's, stay tuned. Please tell your friends to watch, comment, and like, and I will see you all tomorrow in class. Bye.